This meeting is being recorded.
Good morning, everybody. This is Gary Moyer. I'm the technical chair for the American Institute of Aeronautics and Astronautics, Los Angeles, Las Vegas section. And this morning we have a presentation by Scott Kidney of ATA Engineering, who's a applications engineer for the product. And Scott Thibault will introduce us. Scott is involved in the sales and presentation of the software, and we're going to let them take it from here. We'll come back later for Q&A, and we're looking forward to an interesting presentation on the deployment of panels and devices on spacecraft. Okay, Scott, it's yours.
Very good. Thank you, Gary. This is Scott Thibault from ATA Engineering, and I am going to give a quick overview of who ATA is before turning over the podium, if you will, to our technical presenter today, Scott Kidney. Today's presentation is on system simulation for deployable space systems, and is based on a piece of software published by Siemens Digital Industry Software called AIMSIM, A-M-E-S-I-M. AIMSIM is a systems modeling tool, and I'm going to give a brief introduction to the AIMSIM tool itself, while Scott is going to go into more depth and actually do some live simulations in AIMSIM of aerospace-related systems, including deployable space systems. So who is ATA Engineering? ATA Engineering is an employee-owned small business with a full-time staff of almost 200. We are comprised mostly of degreed engineers, a great number of AIAA members amongst our staff, and many of them have been recognized as subject matter experts by AIAA, SAE, and other professional societies. Our forte really is providing high-value engineering services to help our customers solve the toughest product design challenges. Our principal markets are aerospace and defense, including air-breathing transportation, but also launch vehicles, satellites, deployable space systems, space stations, and other related equipment. Also robotics and controls. I'm proud to say that ATA Engineering has over 55,000 engineering hours into the Mars rover project under a contract we had with JPL. We also work in the areas of industrial and mining equipment and themed entertainment. There's a surprising amount of engineering that goes into roller coasters, themed rides, animatronic figures, and that sort of thing that we all enjoy. We provide our services from offices across the United States. Our headquarters and principal office is in San Diego, California, but we also have offices in Los Angeles, in the Bay Area, Albuquerque, New Mexico, Denver, Colorado, Huntsville, Alabama, and Herndon, Virginia, outside Washington, D.C. Our principal services are design, analysis, and testing, and we are, in fact, the largest independent provider of ground vibration testing services in the country. ATA Engineering is also a Siemens Platinum level solution partner, and we provide a full range of services for Nastran design, simulation, and engineering products, including AIMSIM, which is also sold under the brand SimCenter 1D, but NX, Nastran, VMAP, Star CCM Plus, SimCenter 3D, TeamCenter, and a great number of other products as well. As a value-added reseller, we provide licensing and support for all of these products. We are also a principal provider for Siemens training. And in fact, the tutorials and training materials for Nastran, the principal Siemens FEA solver, are actually written and maintained by ATA Engineering. And if you sign up for a Nastran class with Siemens, you will discover that it's in Herndon, Virginia, or Albuquerque, New Mexico, or Denver, Colorado, or Los Angeles, or in San Diego, because those are where our offices are located, and you will find yourself being taught by an instructor from ATA Engineering. If you want more information about the AIMSIM product or any of the other products that we sell and support, you can visit us at our website at the link shown here. There's a wealth of information there, not just about the software itself, but white papers, tips, tricks, macros, and other resources useful to an engineer. So now let's get into what is SimCenter 1D AIMSIM. AIMSIM is a tool that is used for 1D analysis. It is kind of a Lego building block method for putting together complex mechatronic systems. It can model all kinds of systems: electrical, hydraulic, pneumatic, mechanical, all combined together in one. And unlike higher level 3D simulation tools, AIMSIM runs typically in a few seconds, even for very complicated systems. So it is used very widely in the automotive industry and in the aerospace industry and in the marine industry for modeling complex systems. It can manage things like fuel economy and energy management, structural integrity and durability. So you're actually, determining whether or not your machine will operate safely. Operability and efficiency, noise and vibration, a great deal others, all within one simple, well, I shouldn't say simple, one very comprehensive tool. So the AIMSIM tool is used for pre-design studies. It is a particular strength for helping you to do what-if analysis and trade studies on systems for which you don't have all the information. You don't have a full 3D model for your deployable space structure. You have a general idea for the area of solar panels that you need to deploy, the weight of those panels, that sort of thing, but you don't have all the details. AIMSIM is a wonderful way of drawing a box around your variables and doing sensitivity studies to determine the most likely configuration for your system that's going to lead to success. So it's used for system sizing and integration, performance balancing, particularly trade studies, to make sure that you have an optimum approach, balancing out all the different design criteria, validating control systems, and connecting in a system model all of the different individual pieces that make up a complex system. These could be hydraulics, pneumatics, thermal, electrical, mechanical, signals, etc., all within a single model. AIMSIM is available with up to 48 libraries of pre-built models. And each of these models is not just a hand-waving, spring dashpot sort of thing. They are carefully validated models with literature to back them up. They're based on semi-empirical methods or closed analytical solutions that allow you to use the models with confidence as long as you use them within the range for which they've been validated. Altogether, there are over 6,500 different multi-physics models that can be used within AIMSIM. And Scott Kidney will be talking about quite a few of them today. So I will like at this point to turn things over to Scott Kidney, who will take over the presentation and begin giving us a few more details about AIMSIM. Now, while Scott is doing that, allow me to say that if anybody has any questions, by all means, write them down. We will have a Q&A session at the end, and Scott Kidney and I are perfectly willing to stay as long as necessary to answer your questions.
So Scott, I'll need you to stop sharing, and then I'll be able to share my screen.
Okay. So there we go.
Perfect. Alrighty, you should be able to see my screen now. Yes.
We can.
Excellent. So starting on our presentation today with AIMSIM and deployable structures, I kind of see deployable structures in two camps, and I'm going to cover the first one here, which is if you do have an existing design with spaceflight heritage and you need to modify it for a new mission, or a new purpose or a new bus that your company is developing, I do realize, and this is true in industry, heritage is key on anything like deployable structures, et cetera. And you may have a lot of models, a lot of analysis, a lot of information already that was done to model this particular deployable structure. But how can you move forward with all that information without starting from square one and modify it for your new mission? So what AIMSIM allows you to do is to tap into all that existing modeling that's already been done. And as you move forward, you have a couple different ways you can work with that existing information to evolve it into what you need to do to support your new requirements. And unlike a coupled simulation, SimCenter AIMSIM uses co-simulation to solve equations, and it'll also work through the SimCenter 3D motion state equations separately. So it's working together with other SimCenter 3D motion kinematic solution products, which is of course the complete Siemens solution to working through something like this. But at the same time, Siemens and the software is written with the understanding that there's a lot of people in the industry that do use atoms for their kinematic solver, and AIMSIM can tie together with atoms in a variety of different ways, as far as either through co-simulation with AIMSIM and atoms, or model exchange between the two software elements. So you can take the existing information, modify it for your new mission, and then move forward. And I understand you're close to heritage and you're keeping it as tight with the same modeling. You're introducing some new analysis software, but you're evolving a good design and bringing it forward to be able to apply it for new missions, new purposes, new buses, etc. The other option, of course, are if you want to start with the clean sheet approach, and you're either at a satellite startup or you have a completely new idea and you want to start almost from a napkin sketch of, here's your idea, how do we start with nothing and move forward, and use AIMSIM to start working through kind of a requirement space, or requirements don't almost exist at this point. You're just trying to see what can you do, what's possible. And AIMSIM fills, I would say, one of the best jumping off points from a napkin sketch moving forward into software, where you don't have to necessarily go through all the work to get like a 3D model and then do kinematic analysis and then electrical analysis, etc. You can simply use one product, Siemens AIMSIM, and start from the basics, right? What you had dreamt up from a napkin sketch, and start moving it forward before you actually then move into some of the more specific software packages to bring your design forward. So this is where we're going to switch over to AIMSIM, specifically moving forward, say, from a napkin sketch. Let me shut this down and switch over. All righty. So here we have SimCenter AIMSIM. There's really three, or I'm sorry, I should say, actually, what we're going to be working with majority is 4 different areas. We have 4 tabs at the top, which control which point in the simulation you are in. You start with generally Sketch. Sketch allows you to work with a clean white space here, and then drag and drop components onto the white space for modeling. You do that by using a number of different libraries that are available through the software. And you can see there's, anything from signal control, hydraulics, thermal, pneumatics, two-phase flow, air conditioning, gas mixture, turbines, powertrain, 2D, 3D mechanical, electromechanical, and so on, aircraft, aerospace systems, etc. So by using the library and understanding what you want to do, each of these libraries has a number of different components built into it that you just simply then drag and drop onto your workspace as far as how do you want to hook items up, as far as building the system you want. As far as, I just built a small tank here with 6 different ports and then a temperature sensor, fixed onto it. That's how fast it goes. So for the solar array, what we're working with today is just a solar array with 3 panels. Each of these panels is modeled at each of these locations here. And then at the connection between each of the panels, and also back to, say, the satellite or satellite bus, there's a pivot joint here that is given, it has some inertia and then given some torque essentially to model the change in position. So once you're through, I guess I've gone through, sketching and modeling here. Next up would be assigning submodels. So there's not only, within each library and the components, there's also within each component, there are sometimes one or multiple submodels, depending on what level of modeling detail you want to capture. Meaning, do you want to bring in pressure effects? Do you want to consider thermal effects? Do you want to consider, many different aspects that some of these, components may have associated with them? And with that, I can click on any one of these, and it'll tell me as far as, which submodel's been already defined. And then it brings up also a window here, external variables. So this is just not, of course, not a, pretty picture in a schematic. This is, a true representation of what's the component and then what are the kind of the inputs and outputs to it. And I'm trying to open up this window here so you guys can see, as far as absolute, so through this component, it's feeding through absolute positions, absolute velocities, accelerations, torques, forces, a number of different items are being, calculated through this particular component as part of the simulation. Third tab, so this is the third step in the solution process, are setting any parameters. This would be a step where you would set up initial absolute positions, inertias, any initial velocities. So this is your boundary conditions, just typing in information as far as where, say, panel 3 would start the analysis and go from there. Each of these models have their own associated parameters. So say the joint has a stiffness associated with it and damping, so inertia, set up in the coupler or in the rotational in the rotation for the joint. So this is where you can parameterize your model, set it up specifically for what you're trying to model. And then once those are all set up and ready to go, you can move into simulation. Simulation first also, it goes through a compilation check first, where it looks at the model you built, sees if there's any errors or if it has any outstanding issues that may require attention. And for this particular system, I don't know, my run stuff is over on the other screen, but it runs just that fast. It went through, let me see, go through it one more time. Starts at 0 to 100%, and it's done. And then from what you can do from there is check on any of these components and see what was done. So for instance, here, panel 1, the position of point 1, which is right by the satellite, it didn't change, but the position at point 2, did change. It folded out. This is a 12-inch panel, and it folded out away from the satellite to its full extension of 12 inches. Took, in this particular analysis, about a second, 1.1 seconds. I can't really see what that is, so I'm gonna, right here we are. So I can put on, I'm at 11.99 after 1.16 seconds. It's just that easy to create plots of what's going on. Panel 2, so its point 1 was at 12 inches following that, but then, I'm sorry, point 1 was following point 2 on panel 1. Panel 2, point 2 is out at 24 inches. So you can kind of see where it went through the animation and how its position changed throughout time. Same thing for panel 3. I'm going to just clear this, start with a new graph, whereas its connection to panel 2 made it out to 24 inches, and then at the endpoint way out here, it's at 36 inches absolute position. And you can go through and say, okay, so a number of things you can get from an analysis such as this is, as far as the time it took to open up, and of course, these are all pieces of feedback that are calculated through the analysis. Your velocities, spring torques, it's already calculating because it is time-based. Any kind of transient that might be in the joint due to opening up or to that motion or hitting a stop, etc. And the other thing I just wanted to see was, I think it was, just output torque. Output torques are constant. Signals are constant. So all the information that you could just, find out about panel extension through just a real simple model. So moving on, one thing, this is a solar panel that we're working with. Wanted to also just show, on this panel, there's of course an array of solar cells, and there's a lot of information as far as how much energy is being developed, what models are present in the software. So we're going to back up again to the sketch phase one more time, where just a simple model was created. Certain submodels were chosen on these particular components. I believe they're quite simple. Not a lot of specific, different types of submodels are related, but the parameter section is quite significant. And right here, we do have, for the solar cell, a gallium arsenide solar cell being modeled. And what makes this a gallium arsenide solar cell is the specific energy gap at 0K value here, and then the energy gap fitting parameter A and B. So these are specific to that type of solar cell. So if you do have, of course, a different chemistry for your solar cells, you could go in. This is a generic, solar cell like library component. You can adjust it, based off of what your specific chemistry is for your solar cell that you're using, and then enter the specific values. Either if you're making it or you're having it purchased, enter your specific values for that particular cell. And then this particular analysis is set up such that once you do have the parameters, this is set up to look at how do the various parameters, how can they change by sweeping certain values through set of of values such as temperature, diode saturation current, et cetera, and looking at these parameters, sweeping others through a certain range of values. Those are all done by, just setting up design studies that, you can see with all the parameters we just discussed, how some are held constant for a set of 3 analyses, but then, such as this constant value, I believe this is temperature, is swept for that design study. And then what happens next is it's held constant while another one of these parameters is swept. So it allows you to do a quick design study just by simply, naming, defining parameters, then working with defining a study as far as how values are swept. Again, we're going to run the solution, and as you would kind of suspect, it's going to be doing 18 different analyses, but because this is a 1D system, relatively simple, this goes relatively fast. And as this finishes up here, I'm just going to pull up a couple plots that have been predefined here so that you can see them. And this is an example of, on a solar array, the temperature effect on cell performance, and how does, as temperature increases, the semiconductor band gap shrinks. It causes an open circuit voltage to decrease. And this kind of, shows the effects of the solar cell with respect to temperature. And then there's other, things that, were done as part of this design study as far as irradiance. This expresses the radiant flux received by a surface per unit area. So you can see how that changes with respect to, different settings on the various parameters. So you can, almost, take this model, compare it to literature on the solar cells you've selected, and make sure it's behaving correctly once you go into modeling. So just, quick, this is excellent for, building up, different iterations on parameters and seeing, how do different things such as temperature, pressure, et cetera, affect the performance of the various components in your system. So moving on, next thing would be, I have a solar array. I have it extended. I have solar cells on it. They're getting, this much solar energy. What one could do then is plug that information into an overall system model of a satellite. And what's great about this is you're not just talking about just the solar cells or the solar arrays, but how is that supporting the energy being delivered by the battery with its regulator, and then of course the various electrical loads on the satellite, be it mechanisms, propulsion systems, communication systems, etc. And you could take the information that you have from your cell and your solar array, plumb it into a diagram such as this. I'm just going to run it. And again, this is something that, it's library components with a lot of information and a lot of physics built into them that, model very closely what you would typically select from catalogs. And you could see, say maybe solar irradiance as you're going through, particular orbits, or, and how it's dropping off, at different areas of the orbit. And then, a power analysis. I'll bring it over here too. as far as what's being provided by solar arrays, batteries, and you can see the battery fill as your solar arrays power is dropping off, throughout an orbit. And then total dissipated what power is given by the yellow line. And you can see how all these systems work together, for the modeling using the software. Okay, so one thing I wanted to add, and I'm just going to go back to the PowerPoint before I go on to the next topic, but not only specifically on the solar panels, the software also has the ability to, pull in mode shapes. And we've been talking about kinematics and just, specific positions of panels, etc. But you also have the ability to, incorporate dynamics and pull in the dynamic information from any of your finite element analysis solvers. So if you do get to that point of modeling the system, you like the panel design, you like the panel size, you run that through FEA, you get the modes, you bring it back, and you can put that information into AIMSIM and have, not only, transients, say, due to hinges hitting stops or whatever, while a solar array is opening up, but also the dynamics of the system and how that may affect positions and joint loading. The other thing too is you can go one step further. Instead of a 2D type analysis, you could also go into 3D. And there is an assistant that would allow you to, set up a 3D model, 3D joints with the motorized joints, etc. So maybe you're not doing a solar array, but say perhaps an arm. It does have all the modeling information built into the software to handle arms, different joints, degree of freedom, inertias, etc. That would be necessary for that particular type of analysis. And of course, you could set up an animation that allows you to see how this is moving in real time. Okay, so now switching gears a little bit, and we realize, the needs of the audience, and I guess the audience has different needs. It's just not space flight. There's a lot of people interested in aircraft and quadcopters and other types of flying machines, but wanted to show how AIMSIM would also work with respect to, say, a quadcopter design. So you can kind of see how you don't have to worry about. AIMSIM doesn't just focus on one area of a system, and that's what's best at. It focuses on many different aspects as far as batteries, motors, propellers, what's your lift, how does this behave, flight dynamics, etc. It'll model everything, and that's where it really is strong, and that's what's really strong at. So we wanted to go through just a quick intro to a quadcopter exercise with the software, just to kind of show what's going on. This is kind of state chart driven. Once again, as far as you have a particular environment that you're flying in, a particular mission, and then you have control loops for all the various rotors on the quadcopter, and then you have the quadcopter model and the aircraft model on this right-hand side, so that you do have the control, the mission and the control feeding into each of the 4 motors and the 4 propellers fed by a battery. That feeds into what are the flight dynamics of this particular system for a particular mission. And you guessed it, there's an animation built into here. So the movie will show you the animation of how this flies and performs throughout the category. But you can see a number of different areas being touched here. Once again, we looked at mechanical systems, with the solar array, but now we have batteries, motors, you know, a lot of, you know, batteries and motors and mechanical, which we saw in, you know, solar arrays, deployable arms, but then also now propellers, which you could see in, you know, any number of aeronautical systems. So I'm going to start first, you know, back this up to sketch. And I think I want to go at B in parameters here. Just take a look at this. You're not, this is, a lot of these have additional settings too. So they're just not, you know, going down a chart and filling out information. They do have additional interfaces that pop up and allow you to either import geometry or additional, you know, add additional information as far as, you know, specific airfoils or pitch information with respect to the blade design, say on this particular propeller. There's also information on specific interfaces for, let's take a look at this. So this is using a McCormick propeller performance maps specific for, you know, a certain geometry of the propeller. So it's not just, you know, you're not just strictly relegated to just entering table values. There's a lot of nice user, there's a lot of nice information here that you can enter. And you can see too, this is probably not where you would start, you know, just from a napkin sketch. There's a very layered approach to AIMSIM that you can start with very, very simple models. And the solar cell model is a great example of that, where you can just understand how the various effects of temperature, et cetera, affect your solar cell. And then you can build it up to a much more complicated model, such as, you know, having specific propeller geometry built into, say, a quadcopter analysis or demonstration. So again, we have 4 motors running a quadcopter, and that's this particular analysis. I'm going to run the simulation here. So just like that, I have all the information as far as, you know, what torque is going into each of these propellers for the given mission profile. You know, I have speed, you know, what's the controlled speed, what's happening. And again, plotting is just as simple as dragging and dropping onto this white space here. And of course, measure current, you know, and this is for one particular propeller. So you can take a look at, you know, amps drawn, et cetera, for this quadcopter. So I'm going to go into, you know, you can take a look at some of these predefined plots that, so somebody went through and made, of course, these plots, and you can save them. And then if you do further analysis or further refinement, you can just recall them, and you don't have to, you know, have just simple plots that you're looking at all the time. You can have these save plots and then recall them, and they're going to just have updated information on it so that you can see how, for a given input as far as the XYZ directions, how does the quadcopter respond? You know, what overshoot does it have, et cetera, as it goes through the different flight profiles, and then taking a look also at roll angle, pitch angle, et cetera, to achieve some of these. Also, of course, like I said, you know, it's not just talking about, you know, you're not just tracking flight dynamics, you're tracking a number of things with this quadcopter, as far as, you know, what's the stated charge of your battery potential, you know, what's the voltage drop throughout the whole flight sequence, measured current, et cetera. So it's capturing and running through, you know, as a quadcopter does its motions. Looking again, 3D visualization. This one does have an animation associated with it, which I probably, did I break it? Let's try this one more time. I may have really broken it this time. Cool. So let me just keep going here, but I can see if I can get this back here. Let me see if I have something fun up. So how about this? I am going to let this figure out itself what's going on. And what I'm going to do is go back to the slides. And if I do get this to work, I'll show the animation and see what's going on. But as far as the slides are concerned, let's see. If everybody can see my screen, I hope. Yeah, awesome. So I just wanted to kind of wrap up here a little bit for myself, Scott Thibault, as far as all the contact information for Scott and ATA, of course, is built into, is shown here, and then just kind of move into question and answers. And I'm going to try to get this animation up and going here while we move into question and answers and go from there. So.
Hey, Scott, could you let me take over for a minute? Let's stop sharing while you try to.
Absolutely.
Yep. And I need to make sure I'm on the right page. Yep, I am. So I just did want to mention, since Scott has to fix a couple of things and we have the opportunity, that ATA Engineering is hiring. We are proud to hire AIAA student members and, of course, regular AIAA members as well. We have both full-time professional positions available and also co-op and internship programs that you can learn about here. Just to save some of the students some time, no offense to non-US students, but because we are a defense contractor for the United States, we are only able to hire US persons. So you must be a US citizen or current green card holder to be hired. If anybody has any questions about these things, there will be contacts on these web pages that will be happy to answer your questions. So Scott, if there's no objection, I think we could launch into the Q&A. I've already started answering some of these live. And so I'll start with those while you're working on your system, but do chime in
Sure.
if I, get too far off into the weeds. I try to keep my egregious lies to a minimum. So the first question is, can we use SimCenter to simulate complex systems, i.e. not just one mechatronic structure, but various systems working together? And the follow-up was, to be more specific, my question is, can we use SimCenter, or AIMSIM in this case, to simulate something as complex as an extraterrestrial habitat? Has anything ever been done in this capacity, and can AIMSIM support such systems? So my answer that I put into the chat, which Scott could elaborate on, is that there is no limit to the complexity of the systems you can model, as long as you can come up with all of the inputs required. In fact, even if the models, pre-built models don't exist for what you want to model, let's say biological systems are a good example. We have no biological systems that I'm aware of modeled in AIMSIM. So if you wanted to model a hydroponics plant that's turning carbon dioxide back into oxygen or something like that, you could create a model for it and then tie it into AIMSIM for everything else, for the electrical system, the solar panels, the pumps that pump the water, the filters that filter the water, etc. So you could, if you had a proper model, predict the oxygen level in the habitat, the number of, potatoes or carrots, you're able to grow over a span of time, as long as you have the models for the biological systems that you tie into AIMSIM. How you tie external models into AIMSIM is extremely varied. There's lots of different ways to do it. It does have a functional mockup interface. So if you have a piece of software that supports FMU, let's say, MATLAB Simulink, for example, you could tie your MATLAB Simulink model into AIMSIM using the FMU. You can also tie in models with Excel, Python, or JavaScript, etc., And all of these models can be tied into the existing modules within AIMSIM. So I might have a system that's comprised of a fluid system with pumps and valves and pipe runs and elbows and all those sorts of things. Also tied into an electrical system for the electrical motor that's driving the pump. There might be a battery system with a battery cooling system associated with it and solar panels to power the batteries, a control system that ties around the whole thing. All of these things can be modeled simultaneously. And in fact, the product is designed to model them simultaneously. And let's see, just another follow-up on the same question. I think I answered already. If you add biological systems in with, say, the functional mock-up interface, can they be modeled to interact with the existing models? And yes, that's true. They can be modeled to interact bidirectionally. So your external model for, I don't know, oxygen release per whatever, you know, in your hydroponics garden and potatoes per hour or, you know, whatever, all of those things can be inputs or outputs to the system. Did you have anything to expand on that, Scott, before I move to the next one?
No, I thought that was answered very well.
Okay, so the next question, hold on, is does this model simulate the dynamic XYZ positions of points on the panels? And I'm going to let you answer that one.
Yes, and it right now it's set up to I'll put just really at the hinge positions, and it's more of a kinematic type analysis for this particular I guess demonstration. But I believe you can actually look at other points if that is your if that's your desire. The other thing too is the software allows you to write equations, and based off of those equations are the equations can involve constants and some of the parameter values, and also some of the result values that are part of the overall system, and it'll update those equations as your model is solved. So what I'm trying to get at too is you're not just looking at the results due to the system you modeled. You can actually write your own equations and get your own output with equations based off of the solution parameters or your definition parameters. So there's a lot of information that you can calculate yourself too and pull off of these models.
Terrific. So let me see if we have any other questions from the chat before we open it up live to the folks who are in the library. Let's see. I am not seeing any, so we are available for additional questions. And just before we go to the questions, Scott, can you see my screen with the URLs for the?
Yes.
Okay.
Mm-hmm. Yes.
I don't have the green box around my screen, so I wasn't sure it was.
Oh, yeah. No,
So we're ready to take additional questions in the chat. Oh, wait a second. I think there are open questions. I overlooked something.
Okay, Robert,
so
it was mine. Have you guys modeled any vanilla space habitat? What I mean by vanilla is like 5 or 7 components, and having that as a baseline to start from.
So
that we have, we've been modeling somewhat smaller systems that might be part of a habitat, like the solar panels that we were talking about today. But there's no reason it can't be. We could certainly check with, with Siemens to see if they've done anything more, kind of like a pre-built vanilla model for a space station. To be perfectly honest with you, they're really not, the models are not complicated to build once you understand how AIMSIM works. It really is kind of a Lego building block sort of thing. The thing is that it's great that it runs 1D and it runs really fast, but it does rely on you to have some understanding of the systems that you're modeling. You can't just throw a bunch of Lego blocks together, because each of those Lego blocks have specific inputs and outputs, what we call parameters. So each of them are going to have parameters, and you've got to know those inputs, or at least a range of inputs for those, or your model won't be very accurate. If you do know what the parameters are and what the range of those, make sure the range of your parameters falls within the range of validity for the particular model that you've selected, the results that you get out of AIMSIM can be quite startlingly accurate, because the models are very well validated. But it can be, actually putting the building blocks together isn't difficult, but when you look at the array of parameters that you need for each model, it can be a little bit intimidating. And you might end up in a situation, well, gee, I don't know what the outlet pressure should be. So maybe you construct your model in such a way that the outlet pressure becomes an output rather than an input. And then you look at a range of other parameters and what are the resulting outlet pressures, that sort of thing.
Okay.
Do we have any other questions live? I do have some more in the chat that I will get to, but just to sort of mix it up a little bit, do we have any questions from the audience?
Any question?
I have a question. I don't know if I'm going to be asking it well, but when I'm looking at you putting together these models and taking the different components and putting them together, I'm wondering, where do you get the baseline for that information, like for all the different parts that you're putting together to make a satellite? Do you get that from like computations, or do you get that from like parts that have been built in the past that you've tested, and are you inputting that information into your models? If that makes any sense.
Yeah, so I think there's two different sources for that information. One, Siemens has done a great job of looking at industry and building in as much information as they do have into each of these components. But then, like you saw on the solar array model, there is going to be some information that maybe is part of, heritage or what your employer's previously done that you need to enter, as far as torque values, friction values, damping, etc. That may be a good starting point, but it could also be one of those things that I noticed on the solar array that I wanted to adjust some of these parameters to have like specific opening times for the array, etc. So I almost think too that if you're starting with a napkin sketch and you want to proceed, it's kind of like you can generate these parameters and enter it into the model and see how does the system perform, and then that's your jumping off point to go into further CAD design, finite element design, flow design, etc. So still look at this as you're starting with an idea, you're jumping into the software, you're defining that idea, and then you're starting from that point to do some of your CAD design, your FEA design, etc. So that's how I probably would answer that question.
Okay.
Okay. I've got a question.
Okay, go ahead.
Can you do, like, you guys talked about being able to do like different parameters, like simulation, like different pressures and temperatures and stuff. Can you do like overall weather? Like if I wanted to put my airplane into a hurricane, can I just run a weather simulator on the thing to see all the different types of things?
Yes, to a point. I still think, it wouldn't have the the chaotic winds per se of a hurricane, but I believe you can put in headwinds and different environments, etc., that you want to simulate, the flight into. So, crosswinds, et cetera, I think are all valid.
It's a matter of, look at AIMSIM as a way of studying the response of a system to certain inputs, right? And if you give it a random input, you're going to get a random response. There's no question about it. And, the value of that response might be very questionable. However, that being said, I have myself seen AIMSIM used to model flight path for an electric UAV. And, it's got to take off. It has a certain amount of weight. It has a certain drag, which has been calculated with an external program and fed into AIMSIM as a model. It needs to take off to a certain altitude and fly against, certain winds from certain directions. And so if you think about it that way, you could say, well, how strong a wind can my, aircraft fly against and still have enough battery capacity to safely land when it reaches its destination? Or you could give it a wind profile and say, well, we have, the wind is changeable from time to time. I saw another model of a boat, a ship, actually. People wanted to know how much fuel they needed to load on the ship because it moved between two different European ports. And there were a number of ports of call along the way where it could buy additional fuel if it needed it, but they were really expensive. So like the ports that were selling fuel along this path were outrageously expensive. So they never wanted to buy more fuel than they absolutely needed from those very expensive ports. They wanted to fuel up at the beginning and refuel at the end, but not buy a lot of fuel in the middle. And so people literally looked at weather patterns and wave patterns and current patterns for the path that this coasting vessel would have to take. And then the vessel itself had a model for the power plant and the propulsion system, the fuel load out. Obviously, as you consume fuel, the ship becomes lighter and behaves differently. And they literally modeled the path of this ship as it sailed from one port to the other. A model that in the real world probably took several days or weeks. And they were able to come up with a model that showed that during certain seasons of the year with known, currents and typical weather patterns, that you should start your vessel with, if it's loaded out with so many tons of cargo, you should start with this much fuel and you will end with that much fuel. And if you do have to stop in the middle, you should buy so many tons and no more because it's too expensive. This was all done in AIMSIM with some tie-in to the STAR CCM plus CFD code for the hydrodynamics of the vessel, and the weather information was boiled down to seasonal models. So that's an example of what you might do. It's not exactly the same thing as putting your vessel through a hurricane. But if you could characterize the hurricane to the proper degree, you could certainly study the response of the AIMSIM model to the hurricane and whether it was likely to survive or not. Smart bet, it probably is.
Okay, this is Gary Moyer, the AIAA moderator again. And I'd like to do two things. First is for each of the people who speaks up and has a question, please introduce your name and at least some level of information about what the purpose of the question is. And then secondly, with regards to this latter part of that issue, I think that what we're saying here is that in order to make sense out of an analysis, you obviously have to have a strategy. And here we have a series of pinpoint answers, specific cases, and you need to strategize yourself, your analysis, so that you are able to either, in the case of what we've primarily been talking about, in order to see the final results of an analysis, you need to think through what the sequence of events in the situation you're modeling may be, or in the case of an optimization analysis, you need to think of some kind of a carpet plot that will enable you to find the peaks and valleys or saddles, and find a way to to seek out those peaks or valleys, whatever your goal is. So that's sort of a question. It's sort of a request. And I'm going to turn it back over to the presenters, and you can respond to that or follow on.
So I'd like to get back to a couple of the questions answered in the chat while our folks in the audience are thinking about their next question, so that they don't pile up too much. This next question is by Rashid Jain, and it says, in the model, can the user set input and output parameters they are interested in, as in the case of systems working together, or is that something preset? So each of the models, the 6,500 models that are available in AIMSIM, have existing input and output parameters. So in practice, you would pick one, a valve, an elbow, an electronic actuator, a generator, a battery. You would pick one that had, as close as possible, the set of input and output parameters that you want. If it doesn't exist, you can still create an external model of your own. But I'm going to bounce it over to Scott for further information with this question. Scott, how easy is it to take an existing model that's in AIMSIM, let's say an electric motor, and modify that model to suit my needs? Would I invalidate it? Would it be worthless once I start messing around with it in that way? Or are there cases where it could be useful to start with one of the existing models instead of building something entirely from scratch?
Sure. So there is a number of components that Siemens has kind of recognized that you're likely not to recreate the wheel. You're likely to go to a vendor who specializes in the fabrication, production, and test of a motor per se, and then allow you to bring that in the house. And what they do on the components, and you kind of saw it on the propeller for the quadcopter. It allows you. They allow you to take a component such as that propeller, and then through further user interface picks, allow you to define it exactly to what you're buying and implementing in your system. So off the top of my head are, of course, motors, batteries, and just let my mind, pumps, do have that ability to further define and match exactly what you may be purchasing and implementing in your system. The other thing too is the software works kind of like, almost like if you want to be a test and troubleshooter type person and you want to throw a gauge into your system and measure what's exactly happening at this point in the system as far as, say, pressure or current flow or any number of things. It has all those pieces of information available to you that you just split a line, put in a flow meter of some type, and see what's going on between components if you need additional information.
Terrific. Thank you, Scott. The next question should be pretty quick, and then I'll turn it back over to the audience for live questions. Just a quick question. Does the software platform produce graphical animations? The short answer is yes, it does. The longer answer is you need to be a little bit careful. This is not a finite element program. It is not a CAD program like a Solid Edge or NX or SolidWorks or CATIA or whatnot. It is not an FEA program. So the animations that we produce and show in AIMSIM are intended to illustrate to the viewer the operation of the system. So let me give you an example here. If I go back to my slideshow, you probably saw this slide of an excavator, digging, and so this is in AIMSIM. This 3D animation is right here. Go back to the beginning. It is here within AIMSIM, but the picture is doing, and this CAD almost certainly came from a CAD system like Solid Edge or NX. The CAD came into AIMSIM, but the CAD is being used for this visualization. The motion of the bucket, the forces and torques on the pins, the motor energy required, all of those are AIMSIM type parameters, but the visualization itself is more of an output intended to illustrate a point. How does the excavator dig under certain conditions? So as long as you understand that, the visualization in AIMSIM is quite strong. Do you want to illuminate on that in any way, Scott?
Yeah, could you just stop screen share, and then this is a perfect way to me to jump in and
Find my controls here. They've been hidden. There they are.
awesome.
Stop. Go.
Okay, here we go. All right. Share is loading.
Scott, just a minute. Is anybody drive a Toyota
Corolla.
Corolla here?
Big one in the front.
Car?
No.
No? Okay.
Thank you.
No problem. Go ahead. It's a parking issue.
Oh, okay, no problem. So just to kind of, I needed to just restart the software and then resolve, and things are working good once again. But this is the quadcopter once again, and this is what this is this is just a simple CAD model dragged into an environment. And what you can do is, based off of your analysis or the information that's generated by the solution, you can allow that to set different animation values for this particular scene. So as I run animation, this is what's happening through the analysis. You can see the flight dynamics or the flight program that was specified for the quadcopter. It was raised up to a certain position, and now it's going to go through kind of a left and right movement as far as the flight regimes is going through. A couple repositionings, and then you can kind of see some bounce as it goes through like a position and hold type maneuver and go on. So very simple animations, but you still can see an animation on a scene and what's happening and what are your responses. So again, you're seeing a lot more information perhaps in an animation than, say, a graph of what's the position of the quadcopter as it's doing its maneuvers. It's a lot of information. Again, picture's worth 1,000 words sometimes. So, we already discussed, battery positioning. The other thing too, what you have available to you, you can set up a flight instrument or flight instrumentation type scene here, and just, I'm going to play this for the particular animation, but you can kind of see in just a graphical display here as far as what's the speed of your various propellers, your battery voltage, etc. And then of course, as it goes through the flight maneuvers, what do the flight instruments look like as far as the compass, attitude indicator, vertical. I believe this is vertical speed, altitudes, etc. is digital. So, there's just a number of different ways you can show what's happening, with the system that you're showing and everything like that. So through plots, animations, and this is called a dashboard here. So I'm going to stop this and stop sharing and toss it back over to you, Scott T.
Okay. Just make sure I'm on the right slide again. Oh. So do we have any more live questions before I get back to the ones that are in the chat?
Gary, I saw Rashi raised hand.
Oh, okay. Rashid?
Can you guys hear me?
Yes.
Yes.
Okay, so my name is Rashi. Thank you for answering my questions. I'm a PhD student here in School of Aeronautics and Astronautical Engineering at Purdue. And kind of like what my research is related to is simulating extraterrestrial space habitats and seeing if with the how they behave, how they functionally behave, how the health of the habitat changes with respect to disruptions. And so kind of like my question was are disruptions something that can be modeled into the software? For example, say you have like a pipeline and we have an external model for how the pipeline, like a disruption model for like the aging and the wear and tear of the pipeline over like years. And is that something, like if we do have like a model for that, is that something that can be modeled into the software?
Certainly it can. One of the things about AIM-Sim models is that they're dynamic. They're not steady state models in general. They are time accurate models. And so like an example that I think about is, let's say you have a habitat and it's a self-healing habitat, a space habitat. And it's designed so that if a piece of debris were to, penetrate the hull, it might lose a certain amount of atmosphere before being resealed, just for example. And you want to know how long does it take for the environmental systems of the space station to react to the loss of atmosphere and rebalance the pressure within the environment after the penetration is healed over. That sort of thing would be a great simulation for AIM-Sim. You would give it the instantaneous loss of pressure, how much atmosphere you believe is being spilled out through the hole over a period of time, and then it gets sealed off. So you'd have this pressure loss and then a pressure restoration as the environmental systems correct. That sort of thing could be extended to any other aspect of a space habitat as well. So the systems respond not just to steady input, but to variable input and disturbances, pressure spikes, a wind gust hits your drone. All of those things can be modeled.
And in terms of like simulation, is there like a timeline that we're limited by? So for example, like let's say I have like a robotic structure, then are we like limited to the simulation time periods of like 1 minute, 1 hour, or can we simulate, for example, like 1 month or 2 months of habitat, or say 10 years?
Years could be challenging, but I'll give you an example of a model that Scott built for me for a customer. It's a cooler case. Think about a case holding beer, right? And so glass door, it loses heat through the glass door. It has a certain amount of cooling going on. The product is loaded into the back of the cooler at a certain temperature. Let's say room temperature, needs to be cooled down to 42 degrees or whatever they've decided it should be. And so the case starts out at a steady state, and what the customer wants to understand is, how does the system behave as it's used throughout the day? So a customer walks in and opens the door, all the cold air spills out. I don't know if you've ever seen CFD of this, but it's really quite interesting. The cold air being heavier than hot, it spills out of the cooler, and the customer reaches in and grabs a 6-pack or whatever, and then he lets the door slam. And there's a certain amount of cycle that goes through. You have a certain amount of cold air that's been lost, and you have cold product being removed and possibly warm product replacing it. And over the course of the day, the customer knows, for a certain particular store or whatnot, they know how many times that door is being opened and closed in a day, and how often it's opened and closed, and what times of the day are very busy. What time does the fella arrive with the truck with more beer on it to reload the beer, in the back of the case that's been removed by the customers during the day, and all of that. And you would think that this would be darn near impossible to model, but it is actually possible to model that over a span of a month. The beer being removed, the warm beer being put in, door being open, closed, and assess what the energy usage is required to keep the product at the proper temperature under these different variables. Now you start, the purpose of a model like this is, okay, now let me start messing with the variables. I'm going to put a quick close mechanism on the door so it shuts twice as fast as it did before without taking off any customer's fingers. Or I'm going to create a policy that we only put new beer in the cooler at these times of day. We don't just open it up and start shoving beer in there anytime we want, because the system is more efficient if we do it this other way. Those sorts of things can be done over a fairly long time scale. The reason that they're possible to do is that the transient that occurs when the customer opens the door and takes a beer is relatively short, and it occurs only a few times during the day, right? So these sorts of things, systems of that kind can be modeled. Something that takes years, it's conceivable it can be modeled. What do you say about that, Scott?
Yeah, the other thing I keep coming back to are, we also spoke to that one customer about greenhouses and modeling that. I still think, both off of the cooler example and for example, say, there was information or discussion about, fouling of various heat exchangers, et cetera. How would that performance be down the road? I still think it's, that type of analysis can be done. What you kind of want to do is have an analysis that it gets to a steady state relatively fast. And then you do have like a slow degradation in performance of various modules within your habitat. So as long as you don't have, 10 years of complete transients that are happening that are kind of, really causing a lot of oscillation in the results, you can stretch out, as analysis, much longer. The other thing you might have to tweak too is, what of course is, what's your frequency in analysis or data being written to disk to once you look at your longer analysis times. Just because, a lot of these analysis you're taking a look at are, hundreds of a second, thousands of a second, and if you try to do that for a long periods of time, you just fill up disks. So I think, and I'm going back to say, this greenhouse analysis we're discussing, I think that simulation was over a year because they wanted to see, what was happening with respect to temperature, moisture levels, humidity, and even down, to, what was, how was the soil behaving? How much energy was being absorbed by the plants for an entire growth cycle of a year. So, stuff like this, these longer term analyses aren't out of the question. It's just a matter of like somebody as yourself who really have that need. It's definitely possible.
It's sort of like what Gary was saying before about, you have to have an approach, you have to have a plan, you have to know what it is you're trying to learn and what it is you have for inputs. Let me get back to something
to be said about that also is that most of us here seem to be analysts, and there's also a world of test and then a world of customers' performance observations. And so, like in the case of the beer ice chest, there's a long history of these things being used, and most people just feed it power and feed it beer and don't know the upshot of what the variables are. But you're talking about selecting a set of variables and trying to achieve a certain result. So that strategy is the overall effect or the overall goal of the analysis, and we really need to keep an eye on that, because each of those processes is really quite complex. He was talking about the CFD analysis of the airflow out of the ice chest. Yeah, that takes a specialist and a little bit of work to do. I mean, I could do that, but my finite element analysis might be orders of magnitude off without my knowledge, unless I tie it to a test. So carry on.
Yeah, very interesting. I myself visited that customer that makes the beer coolers, and you would not believe the amount of testing that they do. They've got these environmentally controlled rooms with coolers in them. They're actually loaded with wooden blocks. They're not loaded with beer. But they have automatic door openers and closers that open and close the doors according to the type of patterns they believe that a person would do. They're loaded with thermocouples and flow meters and all kinds of stuff. And they do this because they really had no other choice. There really wasn't a method that could model that sort of thing with any sort of fidelity before. Well, we are running a little short of time, so let me get back to our chat questions so that those questions don't get ignored. The next question is by Ahmad Hassan, who asks, what manufacturing variables can add to the systems? Is it possible to model various material characteristics of prop components, for example, or a manufacturing method if structural components? Well, ultimately, AIMSIM is going to care about more physical parameters. So it's going to care about stiffness. It's going to care about mass. It's going to care about moment of inertia and those sorts of things. So if the material characteristics that you're talking about affect those things, like using a lightweight composite prop instead of, a heavier style, those sorts of things could be fed into the things that the submodels, if you will, that say feed a quadcopter model. So they can be incorporated, they can be accounted for, but not down to the level of detail of like, well, will this prop crack or not? You will certainly be able to get cycle information out of AIMSIM, how many cumulative rotations did this prop make, or that sort of thing that could be fed into a durability model, but you're not going to get the durability directly out of it. Did you have anything to add to that, Scott?
No, I like that a lot. And I think there's certain areas of the software too that are maybe better at others than others that, materials, et cetera, on the mechanical side, I think you answered it, perfectly. There's some areas in the electricity side and the electrical side, like if you wanted to size conductors and then see the temperature rising conductors, et cetera, it will provide some of that information based off of, how much of the environment you can give it. So it just kind of depends on, I guess what sizing information, what material information you have, and perhaps where you are within the model. So,
and what kind of output are you looking from the model?
Yeah,
you knew
exactly.
that you're using a low strength fiberglass prop versus high strength carbon fiber prop.
Yeah.
How does that, why do you care?
Yeah.
It's about how long does it last? How much does it cost? You can actually put cost models into AIMSIM, and you can say, well, we want to look at the cumulative cost of everything, including the materials and manufacturing and launch costs, to put, say, a satellite into space. And decisions that we make about the way we're going to power this system, or the batteries required, or battery thermal management, impact how much the satellite ends up weighing, and that has a huge impact on my launch costs. All of these things can be modeled. So the next question is again from Rashi. Does SimCenter use physics-based models for its simulation or state-based models? What is the modeling approach used within the software? Well, I know the bulk of what AIMSIM does are physics-based models, but does it have a state modeling capability at all, Scott?
Yes, it does have state space modeling, and then I believe a lot of the analysis is built off of bond graph theory. So I haven't exactly peeled back the analysis and all the stages it goes through, but ultimately it's bond graph kind of energy type modeling that happens between all the components.
Gotcha. So the next question is from Randall. Could you interface your program with a Nastran model? And the answer is certainly you can. There are existing connectors between AIMSIM and SimCenter 3D, which is used to run Nastran. And so if you needed, for example, to keep within stress limits for a space structure, and you needed to interactively go back and forth between AIMSIM and SimCenter 3D and Nastran to make sure that the study took into account the stresses and strains on the structure, that certainly can be done. There are simplified ways of doing it right within AIMSIM without tying it out to an FEA model. But assuming you have established that an FEA model is necessary, it is definitely possible to tie that into AIMSIM. The next question is from Dan Carlock. How did it come about that ATA decided to coalesce on the use of Siemens SimCenter products for system simulation versus competing products from MathWorks, Ansys, Dassault, et cetera? The short answer to that question is we did nothing of the sort. We use all kinds of modeling products at ATA, including MATLAB. I can't say about from Ansys, but we certainly use a lot of Dassault products as well. And there's a very simple reason for it. Even though we are a Siemens reseller and we have a great big bushel baskets of Siemens licenses for our staff, our customers often dictate the tools that we're going to use. So if the customer wants us to use Ansys FEA, then we use Ansys FEA, and we have licenses for that. If people insist on using Abacus from Dassault because they have certain very strong nonlinear capabilities in Abacus, then we use Abacus. So we use a variety of tools. The big difference between AIMSIM and other, well, let's say between Siemens and other companies, is that most companies don't have anything remotely like AIMSIM. It really is quite a unique product. We do a lot of work with MATLAB at our company. It really is a great tool when you want to apply a whole bunch of equations to a process or process data in vast quantities. Remember, we're a very big testing house. MATLAB can be great. The weakness of MATLAB when it comes to system modeling is that you pretty much have to build it all yourself. If it's a very simple system, that's great. Or if it's a complicated system and you're doing it for a PhD dissertation or a postdoc work, maybe that's okay too, because you want to yourself understand all the little details. But if you want to build very complex systems quickly without becoming an expert in programming, AIMSIM is a great alternative to that. And if you want to attach MATLAB models to AIMSIM, that can still be done as well. So AIMSIM and system modeling really is it's a unique capability of the Siemens suite of products. That and that AIMSIM can also be tied into these other products like Nastran, like Star CCM Plus for CFD, or any other, like SimCenter 3D Motion for kinematics. It's very easy to tie AIMSIM into these other existing Siemens products. And it isn't impossible to tie them into other products. Certainly you can tie AIMSIM into MATLAB Simulink, and I'm sure that there's ways of tying it into Abacus using SimCenter 3D as a front end. There's all kinds of ways of working. But I don't think it would be an exaggeration to say that we have hundreds of engineering products at ATA that we use. Some that we use more than others. I would say that the Siemens products, for all kinds of reasons, are our principal tools, but we do have a lot of other tools as well. For example, on the acoustics side of things, we use a product called Wave 6 from Dassault because we found it has certain capabilities in statistical energy analysis that no other software can provide. So we're happy to use the right tool for the right product or the right project, but also we end up using the tools that our customers want us to use.
Great answer. Thank you.
Okay. And I'm just, let's see, I'm just closing out these questions. The last question in the chat is from Randall, which is good because we're running out of time. Is for the beer cooler example, do you use a variable step algorithm? Gonna have to flip that over to you, Scott, since you built the model.
So the beer cooler, so I don't exactly, so I'm kind of hedging here. What do you mean by variable step? If you mean it from the solution engine side of things, I believe, yes, it is a variable time step solution sequence. As far as how the model is actually put together, I believe it is a mixture of, I'd say the thermodynamics are definitely steady state, but then you do have some transients built into that model as far as what's going on with the heating and cooling. So it's just a full live time transient analysis is really what's happening there. And of course, the solver's smart enough to, run multiple core and of course have variable time stepping in the solution sequence. So.
Very good. And we are at the end of our time, and I'm afraid that I myself have a hard stop. And we're there. So I'm going to turn things over to our hosts and go from there. But I'm afraid I'm going to have to drop off at this point in time.
Thank you, Scott. Gary, are you there?
Yes, I just came back on. And okay, so we'll video too. One question I have is, have you presented results such as this at the Aerospace Launch Vehicle Space Systems conferences that typically occur in June?
My response to that would be not using AIMSIM. I believe we typically do have. I can't say for that specific conference, but we do have a number of different conferences that we do present results and projects at. I just don't know if that specific one is.
I know that ATA has made presentations there for other purposes.
Sure.
So, in fact, when I was at TRW and they acquired the Hamilton's propeller company, we got involved in developing a Scimitar propeller composite analysis program. Sure. And the graduate student became PhD from UCLA who was supporting us, did go to ATA in San Diego. So you guys have a lot of capability over the course of 30 plus years.
Mm-hmm. Yeah, it's a great environment. Just a number of different products a number of great customers that we are fortunate enough to support, and it's a very it's one of those types of jobs you just don't know what you're going to walk in today and perhaps get to work on. So it keeps you on your toes, but at the same time, just the variety keeps it a very fun job. So
yeah, that variety and stretching your fundamental engineering principles
exactly
is really a key part of an interesting career. For the sake of those that are maybe watching the array of the gallery right now, in the background and at the library are about 5 members of a Korean team that is working at a local university. There's a professor and several students. And I don't know if Ken would like to introduce any part of that, but I think it's interesting to note their presence and welcome them here.
You want to say a few words?
Ken?
The camera shy.
Okay,
Yeah, so, yeah, I think they're okay, they're okay.
okay. I just wanted to acknowledge their presence. And it seems as though we've come to the end of our time, and looks like Scott Thibault has already bailed out. Okay, I did have a question or comment about the design of experiments in the analysis, particularly the methods I was involved in developing included buckling of panels and post-buckling behavior. And we had some highly nonlinear functions that would develop out of that, where very often our solution methods would get bound up in infinite loops. Increase the stress, it buckles. You don't have enough strength to support what the load is. Decrease the load, and it becomes stable. And you could bounce back and forth across that environment until you put an artificial stop in it or ran out of time. That doesn't seem to be a problem here, with the exception of your results are going to represent that kind of behavior. Any comment about that, Scott?
So I think, I think those pitfalls still are there, depending on, what software you use. And again, with the AIMSIM product specifically, and then Siemens in general, this is kind of a multi-layered analysis approach to optimization and analysis such as that. So my point is in AIMSIM, if you do choose a parameter or a value that you sweep over a range, I still think you can kind of get caught up on local maxima or local minima, and you do have to be, as an analyst, aware perhaps what's going on with your system, what are the physics, and identifying maybe even that you're on a local maxima or minima. But like I said, a layered approach, though, Siemens does produce an optimization product called HEEDS, and that particular product, when you watch it do the analysis, it's not just sweeping, it's actually, taking large jumps during its solution sequence, so that it does not get caught on a local maxima or minima, or it can at least identify that. And it's a far more robust sequence that it uses, so that it doesn't get hung up and everything. So that's my only thing, is that, and I didn't have the time to go run through it today, but there's a number of different ways to optimize with this particular software, and I think as a good analyst, you got to recognize that sometimes your simple optimization may get caught up, but there are ways to get around it using different tools. So
very good. Okay. Well, I guess we could, in the matter of Robert's Rules of Order, I guess we could have a motion to adjourn the meeting. And I think Dan Carlock popped his hand up with that one. Randall, nope, that's my mouse. Indeed, I think that's. I'm going to toss it back over to Ken for a moment. And is there anything else you need to do to close out the recording or the other activities?
Okay, so let's start the recording now, because the presentation is finished.